Good morning. In this presentation, I would like to talk about a research project in which I'm interested, using short peptides to mimic natural enzymes. The ability of an enzyme to fold into a structure depends on its primary amino acid sequence. The three-dimensional structure is crucial for defining a microenvironment with the properties for catalysis. Self-assembly is a phenomenon present in nature relying on the spontaneous organization of simple species into complex entities. And the ability of certain peptide-based molecules to self-assemble into ordered nanostructures is well established. In this bottom-up approach, due to non-covalent interactions, the resulting material can possess characteristics similar to natural enzymes, such as substrate recognition and specific microenvironment for catalysis. But among the non-covalent interactions that collectively generate stable assemblies, pi-pi stacking plays a special role. These powerful forces, as exemplified in the short peptide motif of diphenylalanine, can be sufficient to enable access to a wide range of nanostructures. The self-assembly of a peptide is a hierarchical process where three peptide molecules self-assemble into one-dimensional aggregates, which then form fibrils that wrap around larger fibers intersecting to form a gel. In the case of peptides, self-assembly and catalysis can be regulated through the side groups of amino acid residues, depending on the pH of the reaction leading to fibril formation. Tripeptides such as FMOC-FIFI-IS have been proposed to perform catalysis, but the potential in vivo toxicity of groups such as FMOC in biomaterials has also been suggested. And to determine estera's mimicking capacity, the hydrolysis of paranitrophenylacetate is followed, which is used as a model since its hydrolysis yields paranitrophenol, a yellow-colored compound that can be monitored by measuring absorbance at 405 nanometers. The first example of an unprotected tripeptide containing IS that forms a supramolecular hydrogel is L-IS-Diphi-Diphi. The hydrogel is thermoreversible and it catalyzes ester hydrolysis. Therefore, studies were conducted by modifying the termini and observing how the behavior in hydrogel formation and catalysis varied. And by testing each of these peptides for self-assembly and hydrogelation, where the tripeptide passed from its anionic form to its biterionic form, the mediated compound showed the best behavior as a catalyst, surpassing the heterokaryotype IS-PP with free ends with a faster gelation kinetics. So, having highlighted the improvements in both gel formation and catalysis for the amidated compound, the objective of the research project is to synthesize the tripeptide amidated in solid phase and the hydrogel, but our challenge is the hydrolysis of amide bonds, which are more stable than ester bonds. Catalytic activity will be studied using various substrates and catalysis measurements will be conducted at pH 7. For each peptide concentration, hydrolysis will be monitored at increasing substrate concentrations and absorbance measurements at a wavelength of 380 nanometers will be taken as a function of the concentration of the formed product. Finally, the ratio between the catalysis constant and the Michaelis-Menten constant will be obtained, which is an evaluation of the peptide's ability to catalyze the specific reaction, and it can be used for comparison with literature data. Thank you for your attention.